Okay, this lesson is a lesson on doing some simple equilibrium calculations. We're going to take a look at three different questions. This one will be the first, second, and third. We'll get a little bit more difficult as we go. So the first question asks, states the equilibrium equation for the formation of ammonia is nitrogen gas plus 3 parts hydrogen gas gives you 2 parts ammonia. Now at 200 degrees Celsius, the concentrations of equilibrium are as follows. Nitrogen gas concentration is 2.12 molar or 2.12 moles per liter. Hydrogen gas is 1.75 molar. And ammonium gas is 84.3 molar. Molar means moles per liter. So now what we need to do is calculate the equilibrium constant at 200 degrees Celsius. Remember, it's very important that we state that the temperature at which we're calculating these equilibrium constants, because temperature, we do know, changes what that constant will be. It will redirect the equilibrium one way or another. So remember, going to do a simple calculation like this, we need to set up our proper equilibrium expression, and so K, which is our constant, is going to be equal to our concentration of ammonia at equilibrium. Now, because there is in the chemical equation a coefficient of 2 in front of the ammonia, then the exponent in the expression needs to be to the power 2. Subsequently, there is a 1 which is understood in front of the nitrogen gas, and so there's a 1. The nitrogen gas concentration is to the exponent 1, and a 3 in front of the hydrogen gas, and so the hydrogen gas concentration is to the exponent 3. So once we've got that determined, now we can just plug our numbers in. So we substitute our numbers for our concentrations, and we plug and play, and we get a value of 626. And of course, whenever doing these questions, we always finish the question off with a therefore statement. So therefore, at 200 degrees Celsius, the equilibrium constant for this reaction would be 626. We're not going to bother with units. So make sure you take a second and you go through that calculation with your calculator and make sure that you can get it to work. One issue that many students have is they type in their calculator exactly the way they see it here, and they put their exponents on the outside of the brackets, and that can cause a lot of problems. So don't do that. Make sure your exponents are on the inside of your brackets. Now, for the next question, right here, we have a different reaction. For the reaction of carbon, say in coal, and hydrogen gas being mixed, we can make methane, natural gas. At equilibrium, we have a concentration of methane at 84.5 moles per liter, or molar. If we know our K value, which is 5.35 times 10 to the 8th, for this reaction at a specific temperature, we want to calculate the concentration of hydrogen gas. So what we're doing here is taking a formula like this and rearranging it, and that's all we're doing here. Pretty straightforward. So again, our first step would be to determine what the equilibrium expression is going to look like, and so we do that at the top here. So our equilibrium expression, which we actually know the value of, and that's the value here, is equal to our concentration of our methane divided by our concentration of our hydrogen gas to the power 2. Now, why didn't we include carbon? Well, look at the state of carbon. Carbon is a solid, and because it's a solid, remember from our subsequent video on writing expressions, solids cannot change their concentration due to the fact that their concentration is based on density, and density of a pure substance cannot change. So what happens here is that we don't worry about any values for carbon. and because there's a 2 in front of the hydrogen gas as a coefficient, that becomes our exponent. So what I've done here is, because we're looking for hydrogen gas, I've moved it up, cross-multiplied it up, and brought the 5.35 times 10 to the 8, the value for K, down. So hydrogen gas is equal to the concentration of methane divided by the K, value for K. The only issue here is that in this expression we have our concentration of hydrogen to the power of 2. We want the concentration of hydrogen by itself. So in order to do that, we take these two numbers, what we are going to divide, and we have to square root that, or put it to the power of 1/2. And so when we do that, we get a final answer of 1.26 times 10 to the minus 4 moles per liter. And so we should be, that's what we'll get there. So again, remember, the one glitch that people might have is when you cross multiply, do not forget about your exponents. You do have to get rid of those in order to solve for this this answer properly. Now the last question is a little bit more intricate. We have, at a certain temperature, a mixture of hydrogen gas and iodine gas was prepared. We placed 0.1 moles of each gas into a 1 liter flask. Now right off the bat, because we're dealing with a 1 liter flask, we know that to get the concentrations of each, it would be the number of moles divided by 1. Alright, and we can see that from our ice table here. I've got that established right off the bat as my concentration, 0.1 moles per liter. Now after a period of time, the equilibrium that you see here was established. Now at equilibrium, it was determined that the concentration of iodine gas was 0.02 moles per liter. We want to solve for the value of K at this temperature for this reaction. So number one, we're going to set up our ice chart, and again we have to use moles per liter. So if we use, say, a 2 liter flask, we would have taken the number of moles and divided it by the volume, which would have been 2, which would have subsequently cut that in half. But that's not the case here. Pretty simple. Number of moles 0.100 in a 1 liter flask. That gives us initial concentrations of hydrogen gas and iodine gas at 0.1. Of course, we did not start with any hydrogen iodide gas. So what we need to do is determine what the change is going to be along the way, and from that change then determine what the equilibrium concentration is. Now we know that we went from 0.10 moles of I2 to 0.02 moles of I2. So if I take 0.1 moles and subtract it 0.02 moles, I will get my change. And this is pretty straightforward. And so when I do that, I find my change to be 0.08 moles per liter. That's my change in concentration. And it just so happens that the concentration change of I2 and H2 are going to be the same. And so they are both changing by minus X. So in both of these cases, we have the same amount of change happening, and it's 0.08 moles per liter. Now, for every 1 part of hydrogen gas or iodine gas reacting in this reaction, we get 2 parts hydrogen iodide gas. So our change here is going to be plus 2x because we have a 2 out in front. Notice how I set up my equilibrium reaction. So that means I would take whatever x is here and multiply it by 2. As you can see here in the calculation, so I get 0.160 moles per liter as my change. So the most important line, my equilibrium concentration line, will then be as follows. My final concentration of hydrogen iodine gas, 0.02 moles per liter. My final concentration of hydrogen iodide gas is 0.16 moles per liter. So now I can start to determine what my equilibrium law expression is going to be. And so I set this up using my equilibrium concentration chemical reaction. So it's hydrogen iodide gas to the power of 2 due to that 2 in front, times the concentrations of my hydrogen gas and iodine gas. All these concentrations, of course, at equilibrium. So we can see how that was all substituted in. And then we get our final answer of 64. So therefore, the value K, big K, for this temperature is 64. And there you have it. Those are 3 simple calculations that can be done with simple equilibrium equations, where my X is still a fairly large change. In the next set of lessons, we're going to take a look at how you would calculate these problems when X is really, really small.